Hi everyone, this is Vikram from Gigayasa Wireless. This is an introductory lecture on software-defined radios. These are the contents that we are going to cover in this course. So let's jump on to what are software-defined radios. So software-defined radios are nothing but radio communication systems that are used for transmitting data from one device and then receive the data on the other device. The important question we have is how are they different from the traditional hardwired radios? So this is the answer. So a software-defined radio is a hardware where the functionality of some of the modules can be controlled using a software part. So what does that mean? So we know that a SDR consists of many modules, many components. And those components are your mixer, they could be your power amplifier, they could be your digital to analog converter, or they could be your buffers for transmission and reception of data. Now, the parameter related to all these modules, the carrier frequency for the mixer, the amplification for the power amplifier, the sample rate for digital to analog converter or analog to digital converter, and the size of the buffers for transmission and reception of data, these parameters can be controlled using some software-defined APIs. So that's what differentiates a software-defined radio from a traditional hardwired radios. The other question is, why do we require software-defined radios? So answers are simple. A fixed functionality radio is very expensive and it cannot be repurposed. If it is built for one application, it has to be used for that application. Whereas software-defined radios, you can actually do multi-band operations using the same radio itself, as long as you are performing the exactly same operation. And you can use them for different applications. You can use the same radio for cognitive radio purposes, or you can use the same radio for military radio purposes. You can use the same radio for designing and testing your algorithms for, let's say, Wi-Fi. And the same radio can be purposed for testing of algorithms for cellular networks. So they are very adaptable and they are very flexible. The next one is, now we know that in general, systems consist of two parts, software part and hardware part. So hardware part could be your radio and software part could be your digital signal processor. So one can upgrade the software part of it and they can save the amount of money that somebody has to invest to buy the hardware again. So that allow you to reuse the same radio for some modern applications as well. The third one is, let's say if I am designing an algorithm. So if it's a hardwired radio, first of all, I have to prototype that algorithm into some low-level language, something like VHDL or Verilog, and then put them into the hardware and then test the performance. Whereas the software-defined radios allow you to design the same algorithm in a high-level language, something like Python, and then integrate your radio with the system, and then check what sort of performance are you getting. And if you feel that, okay, there are some limitations in that algorithm, think about them. Make the updates in your algorithm in a high-level language itself, and then iterate over the whole process multiple times till you get a really good performance. So these are the other advantages that software-defined radios offer you. The last one is, I think we can easily understand from the first three bits that it significantly reduces the cost. Now, how does the functionality or how does the implementation of a typical SDR looks like? So this is the architecture of one of a very simple software-defined radio. Actually, this is an architecture of Pluto-SDR designed by analog devices, which is a really good SDR in my opinion for amateurs. Now, one can see it consists of two parts. One is the signal processor part, other one is the radio unit part. Now, what are these components? So one component that we know is analog to digital converter, which is on the transmitter side, and the counterpart it on the receiver called as digital to analog converter. And how much accuracy we get for a DAC and ADC depends upon what sort of dynamic range do they support, how many bits do they require to represent a specific sample, specific IQ samples. The next one is the mixer, which allows us to modulate a signal over a high frequency, which is suitable for transmission and reception. Third one is power amplifier, which we use at the transmitter side to strengthen a signal before we transmit it over the wireless channel. The next one is low noise amplifier. So low noise amplifier strengthen a very weak signal that our antenna has received so that we can process it further and extract the meaningful information out of it. Then we have automatic gain control. So we know that we have to decide how much amplification we want to give to the received signal. So if we give a very high amplification, we might start operating in non-linear regions, or we might end up amplifying our signal so much that it goes outside the bounds of the dynamic range of our analog to digital converter, which is also not good. That will end up wasting. That will end up in the loss of information. So there are two modes that typical SDR support. One is a manual mode where you can have your own proprietary algorithm and then control the amount of amplification you want to give. Or you can use some inbuilt automatic gain control mode, something like a slow attack or a fast attack AGCs. Next one, we have buffers. So we know that if you have to transmit anything using a radio, we have to insert the data into buffer, and that data in that buffer will be transmitted by the radio. And similar happens on the receiver side also. When a receive antenna sniffs the air, it collects all the information that is being propagated over the wireless channel, and the sampled signal after the receive processing are stored into the buffers. So most of the radios have different buffers for transmission and reception. So they have separate buffer which store samples that are picked up by a transmitter for transmission over the wireless channel, and they maintain a segregated buffer for reception. Now the last one are antennas. So we know that antennas are nothing but transducers which convert a electrical signal into a radiation, and that radiation propagates over the wireless channel. And last one we have is filters. So filters allows us to control the amount of bandwidth that we want to transmit so that we don't cause interference in the adjacent bands. And again, on the receiver side, to limit the amount of bandwidth that we want to process so that we reduce the noise, because antenna can have a much wider bandwidth and we might not require it. And then we might receive some interference in that band. So these receive filters allows us to remove all that part. Next, how do we configure some sort of SDR? Let's say you want to design some algorithm and you want to test the performance of that algorithm over a certain, using some software defined radios. So how can we do that? So we have segregated the whole process into three parts. So first we set up the radio for transmission and reception. And then we set the parameter relevant for transmission. And then in the last, we set up the parameter relevant for reception. Let's set up some basic parameters. So one first thing is we have to give the IP of the SDR whom we are going to connect with this laptop, okay, or system in general. And then we have to configure the sample rates that we are going to use for transmission and reception of the signals, or that we are going to use for analog to digital conversion and digital to analog converter. The next is we set up the APIs for transmitter. So what are the APIs? We have to set the frequency at which we are going to transmit the signal, or this carrier that we are going to use to modulate the information signal. Next is how much bandwidth do we want to process. Third one, how much amplification can, or essentially how much power you want to transmit over the wireless channel. And then these are the other two very important flags. So one is cyclic transmission. So many times it is not possible for us to do real-time simulation, especially when we are interfacing, when we are using a low bitrate interface. So what we do is we load the data in the buffer and we do repeated transmissions. So that can be enabled using cyclic transmission. And then once you are done with the whole experiment, you can clear your transmission buffer and stop the data transmission by setting up the second flag. Now, these are my receiver APIs. So essentially, I will be setting the frequency of the local oscillator and the band where I want to receive the data. So band generally consists of a center frequency that we set up in the previous bullet, and then how much bandwidth I want to receive. So that bandwidth you can configure through this parameter. Then you have to configure the gain control mode, whether you want to set the gain of your low noise amplifier manually, or you want to use the inbuilt AGC functionalities of your receiver to control the strength of the signal that you're going to receive. Then if you are interested in setting the gain of LNA manually, then this variable allows you to set the value of that gain. It can be anywhere for Pluto-SDR, it can be any value between 0 dB to 74.5 dB. Now, last one is you can configure how much samples you want to sniff from the air. And now I'll give you a very quick demo. Here is our tutorial. So as we discussed, so we'll do primarily three things. We will set up the SDR and all the relevant parameters for transmission and reception. We will transmit some random samples using the SDR, and then we will sense the wireless channel and store the sense samples into this NumPy array. So first we will call all the libraries that we require. We require primarily two libraries. One is NumPy for numerical computation and generating the random samples. And the other one is ADI, which allows us to connect our SDR with the laptop. Then these are the parameters we'll be considering for this emulation. So first line allows us to connect this laptop with the SDR, which has this IP address. This is the sample rate we are going to consider for ADC and DAC. This is the amount of bandwidth that we will allow our transmission filters to have or filters to process. We will be transmitting a signal with this carrier frequency, and this controls the amount of power that our antenna is going to radiate. Now these are my receiver parameters. So the frequency that at which we are going to sense, the amount of bandwidth that we are going to sense, the number of samples that we will sense over the wireless channels. And this depends upon your sample rate also, by the way. So now this is our automatic gain control mode. I'm considering slow attack. You can consider fast attack also. So all you have to do is just change this guy to this value. Now, this is some random samples that I'm going to transmit. So I know that the value these samples take is between 0 and 1. So that might not be able to make the best use of the dynamic range of the ADC. So what I'll do is I'll multiply this with 2 raised to power 12. So that means it spread the signal between any value between 10 raised to power 12 to 0. So this allows you to utilize the DR of the ADC better. Now I've configured the SDR into cyclic transmission mode, and these samples I'll transmit using the API SDR.tx. Now, this will broadcast these samples over the wireless channel. Now, this is the line to just clear the buffer. Then this line sniffs the wireless channel and extract out these many samples and store them into the buffer that we have in our SDR. And once the transmission complete, we can destroy the transmission buffer using this API. So this is pretty much all we have. At this point of time, we are not interested in seeing what exactly did we transmit and what exactly did we receive. It's just to see that we can transmit and we can receive something. In upcoming tutorials, we will see how exactly to transmit a specific data and decode it at the receiver. But that part, at least at this point of time, is beyond the scope of this tutorial. Now let's say if you want to have a manual gain control. So what you can do is you can set your gain control mode to manual, and you can give any arbitrary receive hardware gain between 0 to 74.5, and then do the same transmission and reception. And that's it from the demo part. If you have any question, you can go to our discussion forum, post your question there. And if you want some quick replies, you can post in the comment section also. So thanks a lot for your time. See you in the next one. Bye.